x2 is r sin theta sin phi, and x3 is r cos theta. That's the first set of equations. The second set is the inverted expressions expressing r theta and phi in terms of x1, x2. You need to have those explicit expressions. Otherwise, you run into problem and error when you're differentiating. But if you know which is kept constant when you're doing these differentiations. So this is x1 squared plus x2 squared plus x3 squared for half. Phi is tan inverse of x2 by x1. It's the same phi that we encountered in the symmetrical coordinate system. And the theta can be easily written as cos inverse of x3 by r, which in turn is given by then the next step is of course to find the unit vectors in the corresponding to these expressions. And since these turn out to be orthogonal, right, we need to only find the one set of orthonormal basis vectors. Right? So we have already done that in the previous class. We did calculate A1, A2, and A3, and sort of calculated B1, B2, and probably left it at that. But from the fact that it's an orthogonal, you can easily use the formula that relates B1, B2, and B3 does the A1, A2, and A3 and get the result. And in either case, all you need is to get one set of vectors, right? Either the tangents to the coordinate lines or the normal to the coordinates. The other can be easily obtained from the formula that we have given. The most general case, when you need not even have an orthogonal system, but they simplify considerably when you have an orthogonal system. We've already done that. The final result is all I'm going to write down. ER is given by, for doing the analytical derivations, you don't really need to remember what r theta and phi are. You can simply do it analytically. But if you keep in mind that the ER, this is very important when you go to actual problems, when you're calculating normals and area elements and so on. The ER is the vector that is tangent to the R line, and it's also normal to the R equal to constant surface. Right? That's very important to remember. The ER is given in terms of the rectangular Cartesian coordinate unit vectors in like this. We've already derived this. E phi is the same expression as we had for the cylindrical coordinate, and theta is given by cos theta times cos phi E1 plus sin phi. This 2 comes in here in both the expressions. One multiplies it by sin theta, and here is multiplied by cos theta, and then you have minus sin theta E3. Right? Then the next step is also, it would be convenient. So this is when you're doing the want to calculate gradient operator, we also need to express E1, E2, and E3 in terms of ER, E theta, and E phi. So how would you do that? E1, either you can just invert the matrix and get that. Right? The easier way is to realize, since ER, E theta, and E phi also form a set of orthonormal basis vectors for the same space, I could write E1 in this manner. Out E phi times E phi plus E theta. I can write it like this, right? Because since ER, E theta, and E phi form a basis set, I can express any vector in this three-dimensional space in terms of that. But because ER, E theta, and E phi form an orthonormal set, we have a very simple formula for the components, that is a coefficient. And this becomes possible only because we have E theta and E phi from an orthonormal basis set. So if you have this, so can you now tell me what would be E1, the first coefficient? Sin theta cos phi. ER plus minus sin phi E phi plus cos theta cos phi E theta. Then E2 similarly would be given by what would be the coefficient that is multiplied ER. Now I have to go to ER and then ER dotted with E. It is the same as E2 dotted with ER. ER dotted with sin theta sin phi ER and plus what we need is E2 dotted cos phi E phi, right? And then E2 dotted with E theta is cos theta sin phi. And then finally E3 is given by E3 dotted with ER is cos theta. E3 dotted with E phi is 0, so I don't get any term for E phi. E3 dotted with is simply minus sin theta E theta. Right? You just have to make sure run the signs and everything correctly. So this is what it is. This expression will also be useful now. When we go to the gradient operator, which we haven't yet obtained, we need anything that involves a gradient to involve differentiation. Right? So we need to get also the derivatives of the unit vectors with respect to the coordinates r, theta and phi. Now clearly all of the, so I can write star er is 0. The star is any of the three unit vectors er, e theta, e phi. They are independent of r. That will simplify the calculations to some extent. But however, all the three, so E phi is independent of theta, so I can write immediately. All other coefficients, all the unit vectors are dependent on phi, and ER and E theta in turn are dependent on theta as well. Right? So we need all those derivatives. So DER, let's calculate DER by D phi. What is DER by D phi? Right? So can you come to the board and start with? It's just a question of differentiation, but we need to simplify and express in terms of the coordinates and the so that is what we get, right? So we can't leave it like this, because when we are doing these manipulations, we need to express them in terms of the unit vectors in the particular coordinate system I am interested in. And plus, I need to get all these coefficients will obviously come in, right? It will be dependent on the, I have to again express it in terms of the coordinates in the curvilinear coordinates itself. So this is a perfectly useful expression. This is exactly what I want. So dEr by d theta is, we get cos theta times cos phi E1 plus sin phi E2 minus sin theta E3. What is that equal to? It's simply equal to E theta itself, right? dEr by d theta is simply equal to E theta. Right? So let's now calculate the other one. dE phi by d phi is equal to minus cos phi E1, right, minus sin phi E2. Now, how are we going to express this? Is probably the question you had, right? How are we going to express this in terms of? So this is clearly minus of so I get this group of terms here, right? But it's sort of coupled with the other. So effectively, this would involve solving for. I mean, you need to have a method by which to proceed. Otherwise, you might get caught up in trying to how to go about doing this. Is there a general method? I really don't know, but certainly these group of terms appear here, right? And I have to solve for them, right? If you look at it this way, this is one vector, and E3 is another vector. If you look at this equation, right? This is the same vector, and this is another vector. So effectively, I can invert this and express this group cos phi E1 plus sin phi E2 in terms of ER and E theta. That is quite clear, right? Because I can also express E3 in terms of that, right? But I don't need that here, right? So one way of doing it is simply note that this term appears here, both, but it's sort of coupled with E3. But I can always eliminate E3 and get what I want. So the easiest way to do it is to multiply this by sin theta and this by cos theta and add. Right? What do you get when you do that? Right? So when you do that, so I'm going to look at do that simply. So multiply this by sin theta. So I get ER sin theta, right? And I get sin squared theta times cos phi E1 plus sin phi
cos phi E1 plus sin phi
plus sin phi E2, right? So if I add that, so let's just do that, is equal to sin squared theta into that star, this star with this, so that star is cos phi E1 plus sin phi E2. That's what I want. Plus cos theta sin theta E3. Now I multiply this by cos theta, so I get E theta cos theta is equal to cos squared theta into star minus sin theta cos theta E3. So if I add the two, this will get cancelled. So I get sin squared theta plus cos squared theta times that star, which is cos phi E1 plus sin phi E2, is simply ER sin theta plus E theta cos theta, right? So star is ER sin theta plus E theta cos theta. And so I need a negative of this, so I can write this as minus ER sin theta plus E theta cos theta. that's probably the most complicated derivation we need to do for this derivation, the derivatives of the unit vectors with respect to the coordinates. That's what we need. Right? So I can't assure you, that in a general case how you would go about doing it, whether there's an easy, straightforward method, but you just have to inspect the equations and get what you want. Right? Because but in the worst case, if I have, the worst case, simplest would be not even to do that, since what I need is cos phi E1 plus sin phi E2, right? Brute force method, right? Is I have E1 in terms of ER, E theta, and E phi, right? So I just substitute that. Plus E2 in terms of ER, E theta, and I will get whatever I want, right? However complicated the relations are in terms of the Cartesian coordinates, this is the advantage of this step. I have E1, E2, and E3 in terms of ER, E theta, and E phi. And any kind of expression I have, because some I can write by inspection. Right? Because the moment I write this, I immediately see that this is sin theta times E phi. I don't have to substitute for E1 and E2 and get all that. Right? Some you can write the expression, you may not confused as to how it is being related to the unit vectors in the curvilinear coordinates. You just fall back upon these expressions, just substitute it blindly, arrange the terms, and you will get the answer. And so you can try that and you will get the same answer. So then we have the last part, that is write down the answers. We might be running out of time. Theta by d theta can be easily shown to be minus ER, and d theta by d phi is cos theta d phi. So possibly there is a relation here. R by d theta is e theta, d theta by d theta is minus ER. So some possibly relation between this and some similarity between this and this and this. But I'm not expecting to remember any of this. Given the expressions for the ER, E theta, and E phi, you should be able to calculate these derivatives. Or if I simply want you to use them in an exam, it will give you the answer. This is merely a question of properly differentiating and substituting for the Cartesian vectors, unit vectors. That's all there is. Right? And with this now out of the way, we can do the most important quantity is clearly the gradient operator, from which all of the operations involving the gradient of the scalar, the divergence of the vector, and all those which we have done, including being able to calculate the Laplacian of a scalar or a vector. All of it is dependent on this. Right? So we will pay some attention to how to get this. Procedure is exactly the same that we adopted for symmetry. Only now you can clearly see there only two of the derivatives of the unit vectors with respect to phi alone, right, were non-zero. Here we have so many of them, 5 or 6 expressions. That is going to considerably make the calculation more tedious. So we start with this, the brute force method. The brute force method is substitute for E1, E2, and E3 in terms of ER, E theta, and E phi. So I do that. That is already available. The next one is what are the derivatives? D by dx1, d by dx2 in terms of d by dr, d by d theta, and d by d phi. Right, so clearly if I want to write d by dx1, right, this would be dr by dx1, d by dr, by using the chain d phi by dx1, d by d phi plus d theta by dx1 d by d theta. And similarly for 2 and 3, so I can make it x1, I can change it to x2. So if I know how to do it for one, right, I know how to do it for all the others. So what I do is I calculate d by dx1 and express it like this. And simply substitute it here, similarly for d by dx1, similarly for d by dx2. Now if you look at this, for the derivatives, this we already have actually, so this is the same. You won't worry about that. Right? Now dr, this is very similar to rc, but now you have x1 squared plus x2 squared plus another term, so you can easily verify. Right? Basically what we want are these derivatives, that's all. To get to the class. And then it's just a line substitution. Right? So this we have already got, but you can easily show that dr by dx1, right? dr by dx1, 1 over 2 times square root of this is 1 over 2r, right? Times the derivative of that with respect to either x1, x2, or x3. So you get for derivative with respect to x1, you get 2x1 in the numerator, 2x2 for derivative with respect to x2 and so on. So clearly, r by dxi is simply xi by r, but of course now I have to express this in terms of r theta and phi. So it will depend on whether you have, if I have x1, so I simply have x1 in terms of r theta and phi, so that r sin theta cos phi. So this is sin theta cos phi, and dr by dx2 is x2 by r is sin theta sin phi, and dr by dx3 is x3 by r, which is cos theta. So those are already there. d phi by dx1, d phi by dx2, d phi by dx3, we already know in terms of x1, x2 and x3, but we cannot use the same formula, that we won't get the same formula that we got for cylindrical, because those x1, x2 and x3 have to be expressed in terms of r theta and phi rather than rc, phi and z. Derivative with respect to x1 and x2 of phi, with respect to x3 is 0. That is the same what we had, right? But now whatever I get will be in terms of x1 and x2, right? That now I have to express in terms of r theta and phi. The final expression would be different. I will let you to do that. But the thing, the new one is what is d theta by dx1, d theta by dx2 and d theta by dx3. So how do you calculate d theta by dx1? Cos inverse, right? Theta is cos inverse. So you differentiate cos inverse. 1 by square root of 1 minus x squared. If you do that, you can do that, right? It's possible to do that. Yeah. Sachin, can you come to the board and differentiate that? Square root of 1 minus x squared is for, you have cos inverse of x, but here it is slightly different because we have to then differentiate. Yes. And then I have to differentiate this with respect to x1 now. So how do you differentiate x3 by whatever r actually it is? Differentiate it with respect to x1. One of them I have x3 can be taken out because I am differentiating with respect to x1. Right? So what is that? to simplify it, right? Is correct? Yeah. So you have to gather these terms together, but a simpler route, because now I have to express this in terms of r theta and phi. I cannot just leave it like this, right? And it would require a certain effort to do it. But a simpler route is simply to write this as cos theta. A simpler route, I am saying. I am not saying this is not correct. You can go and try to simplify it. You will get the answer. But write cos theta, for instance, as x3 by r. Cos theta is x3 by